Okay, hi everyone, and welcome to the last part of the first day of this symposium. And remember that we have a chat in WhatsApp to ask the speakers questions, okay? And now we continue with the first talk of this part. Our guest speaker is Roberto Flores-Moreno of the Universidad de Guadalajara, Departamento de Química, who has a talk about propagators in information field theory. You can share your screen, Roberto.
Okay, thank you. I will.
And if you are ready, you can go, please.
Yes, thank you.
Yeah, I can see your screen.
Thank you. Okay. Well. In there or studying, I have been quite close because of the friendships and collaborations. So I'm happy also to be today in these celebration days. I remember that when I was a child, they used to say that 50 years make a tradition. So this is a good anniversary, right? It is clear now that UAM is a very important institution in our country, uh, and we actually see it as a traditional place. For example, myself as a physical chemist, I, one of the first places to think about physical chemistry in Mexico for me is UAM. So congratulations. On the other hand, thanks a lot for the giving me the opportunity to be here for organizing this nice symposium. I will talk to you about these propagators in information field theory. This is a kind of learning process I am having, and since it is connected to information theory, which is something I associate to this symposium and to UAM, and on the other hand, I associate propagators to my own interest, I wanted to work out a little bit this connection. And for that purpose, I also had the opportunity to think about how important is the information. It is actually quite difficult to overestimate the relevance of information in our lives, right? It's basically communication and experimentation and learning from our nature around. So I think it's very important, and I like these talks because give me the opportunity to rethink on my way of doing research. Perturbations are inherent to measurement in real life, so that complicates the information and brings us to works like the one of Shannon. By the way, I learned that Shannon's work is 1948, same year Feynman's work, which connects to propagators on the other side, so it was quite fun. The real systems are not isolated, so they present a lot of noise, data is distributed, and some statistical characterization is required. If we look back, quantum theory was born as a statistical approach. We only have to see the titles of Schrödinger papers and others at that time. So also in our everyday life, we interpret densities and things like that as probabilities. But statistics, for me, have been like one part where I am, I need to learn a lot more. I'm missing a lot of learning. I like mathematics, but somehow statistics, because of my own life schedule, are not in the main thread for me. But I'm realizing that I must have learned more. At the end, there are some equations which are statistical or can be reinterpreted in a statistical way. So it wouldn't be bad for me to learn more. And I would like to learn in such a way that I can take decisions. So when I think about information in general, I usually think I need information to take a decision. If I can learn more and more on information theory so that I can take better decisions, then I'm quite interested. So quantum information, for example, is in the postulates of quantum mechanics, they promise that wave function contains all the information of the system. So that's quite nice promise. The next question is how to get it out. When I was starting as a researcher, they teach me that I must do DFT. I actually did DFT, density functional theory, in the PhD. For they were saying that density is a simpler object than the wave function, and that density also has all the information. Actually, that's the essence of the Hohenberg-Kohn theorems, and it's a nice promise. From eventually, in some other place, I learned that density matrices also have all the information of the system. And in some other place, I learned that the Green's functions, or the more general version, many-body version, the propagators, they also have all the information of the system. So in a sense, these objects, wave function, density matrix, propagators, are kind of filters. How do you see, how do you try to see or to understand the quantum system? And somehow I like now the idea to learn more on propagators. I think it's a promising object, but I wanted to connect to information theory, so I found this information field theory term. And on the other hand, these propagators, since I started to study, they are interpreted as a probability. You have, for example, one electron at a given space point, and what will be the probability to find it in another space time point? So these are some topics related to my own research, my students and colleagues. So I am now endeavoring in real time, basically because I want to understand more on the time evolution. I have spent some years of my life learning about stationary states, time-independent Schrodinger equation, DFT, stationary version, things like that. Now I want to complete, in a sense, the picture, to see the time evolution. So this will be more difficult, I feel, in terms of mathematics probably, but probably more funny. I have spent some time, and even today do some calculations on protons, positrons, uh, together with the electrons, in the so-called multi-component calculations for ionizations, for removing, adding one proton, one positron, one electron. And now, uh, for all of them, I have used propagator, Green's function, because uh, it's an approach which is specialized on that. But more recently, I wanted to go to applications, bigger applications, wider, and I learned that people is using Green's functions for doing SAFs, XAFs, SAINs, spectroscopy. For example, I learned that the Koringa-Conrostocker approach to band structure is also based on Green's function. Non-equilibrium Green functions is also Green functions, of course, and there are many, many others. So this seems to be a field which is very rich, and myself, I was not really exploiting all its advantages. On the second point, we have a few papers, and we believe we can improve. So the real point here is we can go not only in the frequency domain, but also in the time domain, and use the complete object, the Green function, to achieve information like the probability of a particular space, uh, time-space point go to another point. So this has a lot of possibilities, molecular wires, uh, There are also self-consistent calculations of propagators which are competitive in accuracy with other approaches like perturbation approaches or some multi-configurational methods. I work in the daemon software. Since some like 20, more than 20 years up to now, I have been co-authoring this code, so I keep working on that. So in a sense, I do my research for developing software, which is useful for chemists. In the path, I have to learn physics. So for this topic, I had to go again and learn on the normal distribution. The first one is the one-dimensional, and the second one is multidimensional. And only to give you an idea how I was not too used to this, um, it was new for me, this concept of the generalized variance, which is a matrix, not a scalar. So I went to that. Then I went to conditional probability. For a continuous distribution, we have a probability like the density, the electronic density, things we use in regular quantum chemistry. And then people can define something like the marginal probability, integrate one of the variables, and then arrive to this last equation in this slide, which is conditional probability. And this equation is in the middle part, you have pxy over the integral of pxy on dx. So this equation has some similarity to equations we find somewhere else, like in statistical mechanics, where you have a Boltzmann factor over the full partition function, which is itself a sum of Boltzmann factors. So this resembles some statistical mechanics distributions. Uh, this is also connected to Bayes' rule on conditional probabilities, which I must have seen somewhere in my early studies as an undergrad student, but never actually used it to achieve some result. So this is, in a sense, new to me, but seems to be something quite important to take decisions on limited information, right? And it's related to variables which are not fully independent. One affects the result on the other. So people has a lot of advances in this direction. It is me who is limited. They use this prior marginal probability and then make a step and obtain what they call the posterior, the conditional probability we are looking for, the one on the left-hand side. It seems to be very useful to make estimates, statistical inference, to take some preferred directions, although not accurate, not fully certain, but they are preferred, more likely directions, right? So I found this works of Enslin. I think he's not the first one, but is one guy who likes this term, the information field theory. Enslin, there is this paper, Enslin from and Kitaura from 2009, and there are some earlier, and there were much earlier works, and before the term they used was Bayesian field theory. So the thing is, in those previous work, they argue that at that time, something like 1950, 75 years ago, the statistical mechanics was reaching a point where this was really acceptable as a statistical theory. And they were starting to connect that. Well, in this paper in particular, this 2009, they take advantage of this similarity and just propose something like this first equation so that, and what it says to obtain, you get an expression which is quite similar. It's actually an expression of a statistical field theory, the statistical mechanics in the field theory approach. That will leave us with the question of what is actually the meaning of that Hamiltonian, of that H in the exponent. And that will be not so easy probably, but it seems to be not really, at first sight, seems to be correct. This middle equation, the last equation also, although we will have to check mathematical conditions, mathematical peculiarities, and to think about the philosophical background on this, because this connects somehow in the bias theory, bias rule, to statistical field theory, and somehow can be used to take advantage of a statistical field theory to make inference if this is fully correct. In the opposite side, it can bring us the suggestion to think more in a basis when doing statistics. Something is not fully clear because usually in statistical field theory everything is quite well defined. It is not an inference calculation, but anyway, they do like this. As you see, these are recent papers, and these are not few papers. These guys have more than 20 papers, I think, in the topic. So I say, okay, seems to be nice. I was recently studying some statistical field theory, so they expand the Hamiltonian in a Taylor-like series, Taylor-Frechet series, because this would be functional dependence. And up to the three terms, the first 0, 1, and second order, are used or can be connected to the study of systems not really interacting. I was not fully aware of this when I started on studying this, let's say December. But it is nice to see, to learn that this will correspond to something like free particle, for example, or free field. They do some, for example, in this slide, when they say assuming d equal to rsn, is an assumption of measurement. There is a signal S, there is a kind of response matrix. There should be a way natural usually where how they are connected, the S, the signal, and the data, which is D here. And as we were commenting at the beginning, there will be noise. So they propose a Gaussian distribution for the prior, for the signal, and then they make some manipulations and end up with a Gaussian distribution also for the posterior, also for the for the result. And in these processes, there are these matrices, which are the generalized variance, the S minus 1, the N minus 1, and then this D, which are named by them as propagators. My feeling is that, I am learning that they are much more familiar to statistical field theory, so they know what they do, why they do this. And the propagator is the word which pulls on me. So then you could do statistical field theory. If you have a partition function, they do some modifications to simplify the mathematics and to extract information. In this approach, the integral is a path integral, which was also new to me and nice to approach now. And at the end, you have, after doing that path integral, in the case of the Gaussian, it is documented how to complete the path integral. The density matrix has some nice properties. It obeys this block equation. It traces the partition function, but this partition function can be also reformulated in terms of path integral. I just was completing my learning on that. And it's closely connected to the propagator. If we think about the time evolution of the wave function, we usually have this U operator. This U operator represented in spatial representation, you get K12, which is a space. One is space-time point, and 2 is a second space-time point. And this propagator kernel K has properties that you can kind of iterate, right? Make the integral a kind of two of them, and you get like a step in a larger time you can divide the step from 1 to 3 into steps and in more steps, and this eventually will lead to the path integral, to the necessity to do the path integral. So you get this as a path integral of the action, and these propagators, actually the Feynman propagator, we have been using in molecules, mainly because its poles are located on ionization energies and electron affinity. So that's the chemistry. I am a chemist, so that's the point of connection. And we have been using this equation in the top, which is Feynman's time-ordered propagator. Manipulations, these are field operators, but we usually span in an orbital, molecular orbital basis, so we bring it down to second quantization, annihilation, creation operators, determinants, and their associated occupation number vectors. And this kind of picture, which we the chemists like a lot, the idea that we know where the electrons are in which orbital, which spin they have. So you can take this as spin orbitals, and then on this kind of images, we can talk about particles and holes on the right side. This goes more to the Fermi picture to avoid having to take care of all the electrons on a big system. So this part is, in a sense, our regular life. We live with that. We do Wick's theorem, but in a version which is downloaded to discrete second quantization operators. But we take advantage a lot of that. Even so, it generates a lot of algebra, and we have to use automatic differentiation software. These kind of operators, there is a super operator defined, there is a metric, and then we get matrices, and eventually we will get an eigenvalue problem, as usual, but this problem has the disadvantage that it is much larger than the CI matrix, CI singles matrix. This is number of occupiers times number of occupiers times virtuals square. So there is a manipulation of the equation. So this is rearranged. So this looks more like Dyson equation. And this Dyson equation, the third one, we use some non-interacting representation, like the Fock effective non-interacting representation, and you get a zero order estimate of the propagator, of the green matrix here, because after projecting on an orbital basis, this becomes a matrix. And the concept of self-energy appears as a matrix on the size of the Fock matrix. And the rest is to make good guesses of that matrix, so you can formulate the quasi-particle equation, which is nice because it suggests that you have a kind of receipt to make correlation functionals for DFT, for example, or, well, nowadays Hartree-Fock and DFT are basically the same thing operational at least. So Hartree-Fock is missing correlation. These propagators provide a way to put it. We have produced numbers for electrons, for protons, and it was nice to create this proton propagator that was quite successful because the second order was very good. In this plot, for example, the blue is the experimental proton affinities, gas phase. The circles right in the top, that is already the combination of electronic structure with proton orbitals. So that's a kind of Koopmans. And the second order brings the red triangles, which are quite good if you consider they are coming from the circles. So that was a nice moment because we thought this is the right physics operating on these molecules. We recover tendencies even from the very Koopmans level. At some point, we did computed nuclear structure on the Yokawa level. I mean, using Yukawa potentials, and we get some information basically with the same Hartree-Fock, but with a potential which is no longer the Coulomb potential, but a more complex one. We are now computing positrons and doing some positron chemistry, which is ephemeral, but is there and is important. For example, for positron emission tomography could be relevant. These are positron orbitals. more and more of that. And we are planning to connect on the synchrotron radiation. I have a colleague working in my same lab, who is Mario Delgado Jaime. He's expert in XAFs and those things. And we want to connect to that. And I think we are more or less close. But on the way, you learn that there are a lot of propagators, advanced, retarded, lesser, greater, and you have to take care because sometimes the authors jump the specification. There are also propagators in statistical field theory, like these ones, and some of them are plainly connected to Green's function, some are not. Some of them, like in statistical field theory, are connected to correlation functions. And because all what we know about correlation functions, this suggests that there is a lot of information there and a lot of connection to other theories. So that was my motivation. On the way learning this more on path integrals, and follow this guy's Hensley to this propagator, which is actually the variance, as you can see in the last formula. But probably what I must say before finishing is that there is also here this Shannon entropy, which here appears basically as the entropy of this thermodynamic picture. And there is another nice point. With some manipulations, they managed to relate the Gibbs free energy in this context to the Kullback-Leibler divergence. So this was interesting for me because some friends like you and some others talk sometimes about the Kullback-Leibler and the Shannon entropy. So it seems to be that there is a lot of future for these objects. We only have to figure out how to extract more information out of them. And well, that's basically what I have to say today. I thought it was important to say to you guys, and I will be happy to try to answer or comment on your questions.
I don't know if he. Thank you so much, Roberto, for your interesting presentation.
Thank you.
Remember that we have a chat in WhatsApp for the questions, please.
Okay. Well, I am in the chat. If something appears, I will be ready.
See you, Roberto.
Yeah. Thank you.
¿Me vas a prestar el de ese para pasarle, verdad? Sí. Gracias.
Hello.
Yes.
Okay. Finally, we have the presence. Finally, we have the presence of the Professor Humberto Galindo of the Departamento de Química, UAM Iztapalapa, who has a talk about informational characterization of chemical hypergraph. Are you ready, Humberto?
Yes.
Okay.
Hope so. Thank you very much, Saul. Thank you for your attendance. Thank you for the interest. I'm part of the organizing committee, so I need to talk the organizing committee for give me the opportunity for this talk. So, but Also, I'd like to say that for the questions, we at the last minute we decide to go to the questions to set the questions in a WhatsApp group, so just to for the fluidity of the presentation. So I will be there at the end for answering your possible questions. So let's start saying. What's the goal of the talk? First of all, I want to mention that some of my work, or my previous work, has been on the applications of information theory tools to the study of quantum systems. But this talk is not part of this work. I'm working on that. But in this talk, I would like to present you some ideas about the possibility to take these tools and put the tools in another context, specifically in the context of networks. So the goal of the talk is to present some preliminary results on two different things. First of all, to analyze a random walker on the hypergraph in different probability regimes. The problem that can be related to this goal is to find or to study paths in the hypergraph. And in a second place, to study the structure of the chemical hypergraph with information theory. The list of characteristics below the point 2, nodes, hypernodes, edges, and hyperedges, are the topological constitutives of the hypergraphs. So they will be clear in the next parts of the talks. Let's start with this question. What is a network? Before we go to hypernetworks or hypergraphs, let's define a network. A network is basically a set of vertices and a set connected by a set of edges. So the magic of this approach for some physical phenomena is that many real phenomena can be captured by networks. Basically, all the things that you can think on as a set of vertices and a set of edges is susceptible to study in using this kind of models. The network science is a growing scientific field, and in this context, several random network models have been developed in order to try to understand what the realistic networks behave, or how these realistic networks behave. In the center of the slide, in the top part, there is a representation of the Erdos-Renyi random network model. At the right, in the top of the slide, this is the Watts-Strogatz model, which starts with a network in a ring form that is randomized by applying some rules. And in the bottom of the slide, the three small networks represent the Barabasi-Albert random network model for different values of the parameter. So I'm not going to present nothing related with random networks, but I would like to say that there is some work running toward these random models. So after that, let's ask the question, what is a hypergraph? And let's say that this is a generalization of a graph. That is, in these hypergraphs, the connections between the nodes are not binaries. I mean, there are nodes that can be related through hyperedges. They can relate more than two nodes. For example, in this picture, the B letters represent the nodes. The hyperedges are represented by the E letters. So, for example, in the yellow part of the picture, the hyperedge E1 relates three nodes, B1, B2, and B3. E2, for example, another hyperedge, relates two nodes, B2 and B3, and this E2 is, this can be conceived also as a binary relation between two nodes. So the graph case is contained in the hypergraph model. The hypergraph model is conceived in the literature as a more general representation of of networks, and then it can be used to study another features present in realistic networks. So the chemical hypergraph, which is actually a relatively new term, it can be conceived as a generalization of the hypergraph. So the hypergraph case is represented in the figure in the D with the letter D. This is the hypergraph that similar to the previous to that presented in the previous slide. And the chemical hypergraph introduces new relations between what we call hypernodes. In this case, for example, in the letter E and in the letter H, these relations are signaled as arrows or as curved lines. So the chemical hypergraph can be conceived as formed by hypernodes, sets of nodes. These sets of nodes, remember the previous slide, in the hypergraph language are called hyperedges. In this context, these are called hypernodes. In a few slides, we can see that this terminology has some advantages. These hypernodes can be connected through edges, conceiving these edges as chemical reactions. For example, look at the letter E in the figure, and the R1 reaction at the top of the slide that relates A plus B and that goes to C plus D is represented as one of the arrows in the letter E in the picture. The hyperedges can be conceived as common substances in chemical reactions, that is, as the intersections between two hypernodes. For example, the R1 reaction and R2 reactions, they have one common substance, which is substance A, and these intersections can be conceived as an hyperedge, that is, a relation between two hypernodes. Let's build the model that we are going to discuss in the next part of the talk in three different steps. The step one is as follows. Let B be the set of all substances of interest, and let N be its cardinality. For example, if we are talking about 5 substances, that is going to be our example, the cardinality is 5. In the step 2, let's build all the possible subsets with N substances. That is the power set without the total set and the empty sets. Another words for this is to construct the combinations of 5 in 1, 5 in 2, 5 in 3, 5 in 4, etc. We will call these sets the hypernodes. And in the step 3, we will build all the edges as pairs of the previous sets. Note that we will consider autocatalytic reactions. Therefore, we will form pairs such that their intersection is 0. This model can be thought, we can conceive an idealized chemistry using the model in the previous slide. For example, if we have 5 substances, A, B, C, D, and E, we can build the adjacency matrix excluding the autocatalytic reactions. That is, the reactions where one substance appears as a reagent and as a product are not valid in this idealized chemistry. It's idealized because all the other relations are possible. That is, we are making abstraction of all the possible chemical rules. There are no rules for the combinations or for the existence of chemical reactions. So it's a very idealized model, but sometimes to understand physics, one needs to forget about physics. So this is the roadmap of the next slides. In the first case, I will present some results of the study of a random walker in different probability regimes to explore the topology of the hypergraph, that is, the edge and hypernode structure. In doing so, I will compute the network entropy and I will show you some plots. In the second place, I will define a set of random variables that capture or trying to capture aspects of the structure of the complete chemical hypergraph. That is, containing all reactions that are possible given a set of substances, as I previously mentioned. I will call this second point as chemical features explorations. And as we will see, is equivalent to say that we are going to explore the internal hypernode and hyperedge structure of the hypergraph. In doing so, I will compute the pairwise Shannon entropy and the reduced marginal entropy, and also I will compute the mutual information. This is the adjacency matrix of this idealized chemistry. So, no, it's fine. No, it's fine. Let's say, for example, that this one that is in this cell represents the reaction in which A becomes B. This one, for example, represents the reaction in which A decomposes into B plus C. And all the ones in this adjacency matrix can be interpreted in this way. The empty cells represent the forbidden reactions. For example, in this cell, let's see, in this cell, for example, which is representing the A plus B that becomes A plus D, this is a forbidden reaction because the substance A appears in the two sides of the chemical reaction. So let's do some what I call topological explorations for this edge and hypernode structure of the hypergraph, and with a random walk. So this is in this slide I summarize the concepts of the network entropy. That is a quantity inspired in the Shannon entropy that has been used to study the topology of networks. In the next slide, I will present you a possible generalization of this network entropy in order to study these hypergraphs. So let's think in one node, let's say node I, and let's think in the walk towards node G. So if Ki is the degree of the node I, we can define a probability of the transition of the walker from node I to node G in the way that is presented at the left of the slide. If the nodes are not connected, A sub ij is 0, and then the probability of this transition is 0 because the nodes are not connected. But if they are connected, that is, if A sub ij is 1, the probability of this transition is the inverse of the degree of the node. The degree is counting how many nodes are connected with this node, with node I. Note that for each node I, there is a normalization condition, because if we sum over all the nodes connected with this specific node I, the result of this sum is 1. For that reason, we can use this quantity as a probability distribution, and then define the entropy for each node in the way that is presented in the slide. This entropy for each node is the natural logarithm of Ki. We can introduce the normalized node entropy by taking the quotient between this entropy of node I over the maximum possible degree, which is n minus 1. I mean, if we think in one network, one node can be connected with all the nodes except with himself. If we have n nodes, the maximum degree can be n minus 1. Finally, we can normalize, we can average this normalized network entropy in the last equation in the slide, and this is the quantity known as network entropy. In the case of hypergraphs, we have a structure into the hypernodes. For example, in the picture at the top of the slide, we can see the node I and the node J, and these two nodes have internal structure, that is, are composed by different substances. For that reason, we can think in another ways to define the probability of transition between the node I to the node J. The first definition in the slide, the 1 over the degree of hypernode I, is exactly in the same way as the usual network entropy. But we can also take into account the cardinality of the hypernode J. For example, in order to take into account how many substances a specific reaction has. On the other hand, we can also have into account the degree of the hypernode J. That is the degree of the hypernode which is in the destination of this random walker. Famous nodes, or I mean, some chemical reactions can be part of different sets of chemical reactions, and then this specific definition of the probability can take into account this thing. Also, we can introduce a parameter, for example, like this beta in the definition of the probability, and we can ask how the model behaves as a function of this parameter, and we can introduce interesting questions like those related with pattern formation, for example. What happens if we limit the size of the hypernodes? For example, for taking into account that the chemical reactions used to have a small number of reactants or products. I mean, we don't know chemical reactions with 50 reactants that give rise to 51 products or so, or things like that. So, using these probability regimes, we want to explore the structure of the edges and its interplay with the internal structure of the hypernodes, specifically with the number of substances. This is one of the plots of these preliminary results. These are the first of the definitions of the probability. And the only relevant thing in this plot is that limiting the number of reactants that can participate in a chemical reactions, which is the meaning of the NJ max at the right of the picture, we can introduce some structure in the network entropy. What does that mean? Maximum implies? We don't know, but we would like to know. So this is the aim of the project. This is another variation of the network entropy. For example, if we take into account the cardinality of node J, we can introduce structure also in the entropy. This has a maximum also. And also, looking at the behavior of these entropies, we can ask of what does the values, these asymptotic values means in the context of the topology of the network. Also, another related questions with this parameter beta is how can it be used to tune this asymptotic behavior, for example. So some questions, some possible questions here is it possible to define a correlation measure between hypernodes? What about a correlation measure between distant hypernodes? Can it be called a non-local correlation measure? In what sense can it be done? How can higher correlations be studied? And the general problem in this type of hypergraphs is the exploration of possible paths inside the hypergraph, because in the context of representing chemical reactions, these hypergraphs can be very relevant for the synthetic design. Let's go quickly to the chemical features exploration, that is the internal hypernode and hyperedge structure. And my goal here will be only to show you some, I think, provocative things, and let's discuss this very, very quickly. This slide presents the basic definitions. These are the discrete versions for the mutual information, I sub xy. This quantity can be expressed as a sum and difference of Shannon entropies, and the joint probabilities and the marginal probabilities are defined at the right of the first line of equations. The entropies are defined in the second line of equations, and just for your information, let's, in the example of joint probability, to exemplify what are we going to do in the next slide. For example, consider a dice with 6 possible outcomes, 1, 2, 3, 4, 5, and 6, and a coin with 2 possible outcomes, 0 and 1. And let's roll the dice and the coin, and then we can have these 12 different outcomes. The specific occurrence of one of these outcomes, we will refer to this as an event in the joint space of the two random variables, or a joint event. So in the old adjacency matrix, let's only mention that we can replace the ones by the result or the outcome of performing these two random variable definition in each case. For example, in this case, the random variable x is built comparing the number of reactants and products. We can have 3 different cases. If the number of reactants equals the number of the products, the outcome is 0. If one is less than the other, is 1 or 2. And the y random variable is built as the answer of the question if A or B participate in the chemical reaction. The 6 possible outcomes are at the right in the bottom of the slide. So let's see, just for informative purposes, that at the left, I present the behavior of the probability distributions of these two random variables, the x and the y random variables, and at the right, I present the Shannon entropies of these random variables. One interesting feature is the asymptotic behavior of the probabilities and also the asymptotic behavior of the entropy. So let's see that one of these entropies has a maximum. So there are few questions about what does this maximum implies or is telling us about the topology of the network. Concerning the joint probability at the top in the left plot, I present the probability distribution. The 6 possible outcomes are represented there. And at the right is the joint entropy. This joint entropy also has a structure that has a maximum, and it also goes towards asymptotic value with n. N is the size of the chemical space, or the size of the number of substances I am considering in this idealized chemistry. In the bottom part of the slide, I present the mutual information of these two random variables. And the physical interpretation of this is that when we go towards large N, if we know if A and B participate in the reaction, we have less information about the relative number of reactants and products. So these are the same plots, but with an analytical attempt using combinatorics. So, the only relevant thing here is that the asymptotic values seems to be independent of my simulation. They appear in the analytical results. Also, these are the same as in the two slides ago. And let's see, these are my last slides. Tengo hasta las 5:10, ¿no? Just to say that we can explore different random variables. For example, we can ask if an individual substance is in the reaction, or 2 substances in the reaction, or 3 substances not presented here. But in the case that is presented at the right side of the slide, there is there is an example of specific structures in the hypergraph. In this case, in red is the B substance, and these 2 chemical reactions are represented in the picture of this part of the hypergraph. And the question here is if this kind of relations present in the hypergraph imply some kind of a specific behavior in these informational tools. So let's say that actually, yes. This slide presents the probability distributions at the left. The 2 plots at the left are the probability distributions. The 2 plots at the middle of the slide are the corresponding entropies, and the mutual information is presented at the right side of the slide. So I don't have physical interpretation yet, but what I can see is that these kind of structures in the hypergraph provoke a different behavior in the mutual information. In this case, for example, it goes towards an asymptotic value. What does that asymptotic value is telling us about the structure of the hypergraph is one of the open questions. This kind of features in these entropic measures are present independent with a independent of which are the random variables that we study. This is another couple of random variables, and you can see that the patterns of the entropies behaves very similar to the previous one. So instead of conclusions, I have more questions than conclusions, but let's try some of them. These informational quantities seems to be sensitive to topological structure and to hyperedge and hypernode structure. Open questions are related to the fact that the systematic parametric explorations are needed to understand more about these measures and what that measures are telling us about the topological structure of the hypernodes. Also, the determination of the bounds for the entropies and the understanding of these bounds. I mean, I refer as bounds to these asymptotic values. These asymptotic values seems to be dependent on which random variables we are studying. So maybe they can have some physical or chemical significance depending on what we are representing in these hypergraphs. Using combinatorics is promising but difficult, among other things, because we need to distinguish one reactant from the others, and this is difficult. We need to define new random variables with physical and chemical meaning, and as I mentioned in the second slide, coming forward, the study of random versions of hypergraphs, a la Erdos-Rengi, Watts-Strogatz, and Barabasi-Albert, and are ongoing. One student that is working in this project is developing the Watts-Strogatz version for hypergraphs. The phase transitions in these models are very interesting questions. Finally, let's acknowledge la dirección de apoyo a la investigación for financial supports and the collaborators with which I have been working in this project. And let's say gracias por su atención. Gracias. Thank you very much.
Thank you so much, Humberto, for your interesting presentation. With this last presentation, we finished the first day of this symposium. We look forward to seeing you tomorrow. Thank you.